let's chat about linear dependence and linear independence. So here's a motivating example. In R2, let's consider the span of these three vectors, 1, 0, 0, 1, and 1, 1. Well, remember the span is anything of the form A1, 1, 0, plus A2, 0, 1, plus A3, 1, 1. Well, frankly, I hope you can see pretty clearly you could build any vector you wanted like that. Let's imagine I wanted to build a vector x, y out of those three. This is actually a nice proof that this R2 is contained in the span, and of course the other way is obvious. Well, how would you do that? Well, it just seems pretty straightforward with this that I would do x times 1, 0 plus y times 0, 1. And can you see that this is just sort of redundant? I mean, yes, you could use it, but why bother? Well, somehow there's redundancy here. And that redundancy is what we call linear dependence. So a subset S of a vector space, think something like this set in here, is linearly dependent if there exist a finite number of distinct vectors, u1 to un, and scalars, a1 to an in F that aren't all 0. These can't all be 0, such that all of these, the linear combination of all of these u's and a's actually equals the 0 vector. So what would that look like in our sort of toy example? Well, can you see that if I had 1 times 1, 0 plus 1 times 0, 1, and then I just took negative 1 times 1, 1, that would come out to 0, 0. So let's just check first component, 1 plus 0 minus 1 is 0. Second component, 0 plus 1 minus 1 is 0. So this set here matches the definition of linear dependence. So I have a slightly more souped up example here. Let's prove that this set here is linearly dependent in 3x2 matrices. How would I do that? I need to come up with non-zero coefficients. Choose A1, A2, A3, A4, and A5 in F such that the following holds. Now, just to be clear, there's always one solution here. There's always the solution 0, 0, 0, 0, 0 equals 0. Maybe the most pivotal words here is, can I come up with a solution that isn't all 0 that will equal a 0 vector? So A1, 1, 1, 0, 0, 0, 0. In fact, maybe you would want to name these M1 to M5 so you didn't have to actually write all this stuff out. But I'll just go ahead and write it all out for starters. We're going to choose A1 to A5 so that this linear combination adds to the 0 matrix. And can you see that component by component, the left side is going to end up being A11 plus 0 plus 0 plus A1, I should say. A1, that coefficient times 1, plus A4 plus 0. And that's all going to end up being 0. So we're going to get a system of equations out of here. This component is A1 plus 0 plus 0 plus A5. This spot the 2, 1 place is 0 plus a2 plus 0 plus a4 plus 0. This place is going to be a2 plus a5, and you can confirm this is going to be a3 plus a4, a3 plus a5. So just make sure you understand that. That gets us a system of equations that says a1 plus a4 equals 0, a2 plus a4 equals 0, a3 plus a4 equals 0, a1 plus a5 must equal 0, a2 plus a5 equals 0, a3 plus a5 equals 0. Okay, so when you have a system of equations, probably the simplest thing you can do is just use elimination. Let's take this equation and subtract that equation from it. Okay, so what do I have? I have a1 minus a1. Those cancel. Then a4 minus a5 has to equal 0. Okay, can you see here? I get that same equation. Here, I get that same equation, right? Since all three of those eliminate to this same equation, that tells me probably my solution is going to work best if I have a4 equal to negative a5. That's really going to happen. But notice that doesn't say anything has to be 0. So let me start with a5 and sort of see where that leads me. So if a5 were equal to 1, say, then a4 has to equal negative 1, right? a3, looking at this equation, has to be negative 1. a4 has to be 1 because I added that to the other side. So a5 is 1, a4 is 1, a3 has to be negative 1, a2 has to be negative 1, and a1 has to be negative 1. And you can actually double check if that was negative 1, negative 1, negative 1, that would put a negative 1 in all the slots. This would put a 1 in all the slots, and they would all cancel. So that is a solution of non-zero vectors that make everything 0.